if we step back and look at kind of the whole tech stack or the whole stack of mathematics that when it started from first principles and landed us at mu p, this is what kind of it looks like. So far we started backwards. We talked about this backwards. So I told you about the mu p's practical benefit first, and then told you a little bit about the intuitions, and then today I talked about some operator norm perspective. Then I talked about this dynamical dichotomy theorem. How do you even derive that mu p is the optimal parameterization? But the proof of this theorem I never gave you. I never gave you like why this picture is the way it is. I just gave you the picture. That was all I said. So great. So yeah. So we just covered this, and for this lecture, let's try to cover as much of this as possible and give you some ideas, some appetizers for what's going on in the foundations. Okay, so how do we prove the theorem that I told you about, like this picture here? How do we know that picture looks like the way it is? Okay, so the key insights come from the foundations of tensor programs. I haven't told you what it is yet. It's just a term right now. But the first insight in this whole area is that every deep learning computation is a composition of two building blocks: matrix multiplication and coordinate-wise nonlinearities. Okay, so as I stated like this, it's almost like obvious. I mean, like that's it, right? Like neural networks, linear algebra is the center of it, and then like all the nonlinearities are coordinate-wise, right? That's a hallmark of neural networks. So just to be more precise, right? Usually when we talk about coordinate-wise nonlinearity, what's meant is that you have a vector v and you apply a scalar function to each entry of v simultaneously. And you get a vector back. Right? That's usually what is meant by coordinate-wise nonlinearities. So here, to say this, to make this universal kind of statement, you need to generalize this a little bit, but nothing outrageous. So we just generalize it a little bit so that we now have k vectors, each of dimension n. Then we can choose a function phi that takes k inputs and output a scalar. And then you form this vector whose elements are just the element-wise application of phi to the vectors 1 to k. Okay, so just a very natural multi-dimensional generalization of this usual notion of coordinate-wise nonlinearities. Okay. Now, matrix multiplication, and what is to be said about matrix multiplication, right? Everybody knows what it is. But here, it actually turns out to be beneficial to distinguish different types of matrix multiplication depending on the shapes of the matrices involved. So, in particular, we'll distinguish between matrix vector multiplication and vector multiplication. So, matrix vector is, you're given a vector, you get a matrix, you form another vector. Right? So the input and output are the same type. Vector multiplication is you're contracting, you're taking scalar product between the two vectors, so you get a scalar back. Okay. Anyway, so nothing like everything is trivial right now. Nothing is happening so far. And then finally, one more step I want to mention is that here you produce a scalar, and I need to use a scalar somehow. The rules I give you doesn't actually allow you to use the scalar that comes from a scalar product. So the last step is that I actually want to, insert a way to use the scalar. So now I just, in the nonlinearities, when I have scalars, I can insert them into nonlinearity like this, where essentially what this means is that every entry of this vector is phi applied to the corresponding entries of the v vectors and all the scalars. So the scalars are shared among all the entries for all alpha, okay? Again, so nothing really is happening so far. Like you might not even understand why this is crucial, but don't worry about that for now. And yeah, and then the final piece of this statement, in order to make it universal, is that you do these computations starting from ID random initialization. That's essentially all of deep learning. And this is the definition, more or less, of a tensor program. So you do these computations starting from ID random initialization. You can compose these however you want. And that will be a tensor program. So what would not be a tensor program is if you have like weird nonlinearities that are not entry-wise. Okay. Okay, so let's look at an example. So I just made this universal statement. So let's instantiate this universal statement on like one hidden layer neural network. That's the simplest case. This is the stereotypical neural network studied in a lot of theory papers right now, and Lanek and others are instrumental in building the infinite width neural network, the mean field network for these mean field limit for these networks. Okay, so let's look at this network. So this is what the network forward pass looks like, right? So assuming input and output dimensions are both 1, you take an input, you multiply by the input vector, you apply nonlinearity, and then you scale the product with the output layer, and you get the output of the network. And then there's another, you apply the loss derivative function to the output to get the loss gradient. Okay, so obviously we are starting from the random initialization. This part is obviously a corner-wise nonlinearity. So here, just to note that like this chunk here is this formulation where phi is not exactly phi here, but the phi here is the phi applied to the product of the two inputs. Right. So anyway, the point is just that like this guy here, every entry here is only depends on the corresponding entry in the vector and xi. Okay. And then finally, to get the output network, you take a vector-vector multiplication. Right. So I mean, again, nothing really happening so far. I'm just telling you that, giving you evidence that the universal statement I made is true. In the backward pass, you can look at the computation as well. You can look at the gradients, and the gradients look like this if you do your chain rule. And again, you can see that like the gradients here are corner-wise nonlinearities applied to the input and output layer weights as well as the scalars. Okay. Okay. Any questions so far? Anybody objects to the universality of that statement? Okay, so let's move on. Now let's look at something a bit more complicated, but there's still nothing really happening. So nonlinear two hidden layer neural network. So I just inserted this n by n matrix in the middle. Again, you will have, this is, just corner-wise nonlinearity, like, right here, when you get the output, this is just a scalar product of two vectors. But in the middle here, we have matrix vector multiplication, where like this guy multiplies by this vector here. Again, like nothing is really happening here. And then let's look at the backward pass, but for simplicity, let's assume everything is linear. So let's look at the backward pass. And you can look at, you can get the gradients and stuff for these parts, but the gradients for the input layer looks like this, which is matrix vector multiplication, right? Where the matrix is the transpose of this matrix, the middle matrix. Okay, so so hopefully that's enough evidence to convince you that like this should plausibly be universal. Every deep learning computation is composition of these two building blocks starting from ID random initialization. But I want you to keep in mind that like really this is universal in the sense that it applies to transformers, apply to CNNs, whatever have you. As long as GPUs are used by people, this is going to be true. Essentially, this statement only depends on people using GPUs. That's the only dependence. If people stop using GPUs, this may no longer be true. But as long as people use GPUs, this is true. Okay, so that's the first insight. It almost looks like nothing's happening right now. We're just making some observation about the expression of computation in deep learning. So you can almost think about this as a Church-Turing thesis, but for deep learning. So this only becomes non-trivial when you combine it with the second key insight, which is that vectors in a tensor program, like produced by matrix multiplication with nonlinearities, when the width n goes to infinity, will have roughly ID entries. Okay, so we'll see how this come about. And in addition, we can calculate the underlying distributions of the ID entries. So this is called the master theorem. When we write down like the very precise formulas for calculating the underlying distributions, but I'm not going to really use this term after this, but FYI. Okay, so to again give you an example of the truth of the statement, let's look at the linear one-hidden layer case. Again, assume input and output dimensions are both 1. So then again the entries of these vectors are ID initialized as is practice. Oh, sorry. And so what you should notice, I guess I didn't have the slides. So when you calculate the output network via vector-vector product, you have a large number behavior if you scale things properly, where f of I will essentially converge to some deterministic number. So the fluctuation of f of I around its limit will vanish as width becomes large. This is just a law of large numbers. Law of large numbers come from the fact that f of I is a sum over the entry-wise products of these two vectors. Right? So when you sum a lot of things which have non-zero mean, then the mean, you're going to pick out the mean of that sum. And then this becomes deterministic in the limit, and then this L prime of f is just some continuous function applied to something that's becoming deterministic. So this L prime will also become deterministic as n becomes large. Okay, so now let's look at the gradient. So this is what the gradients look like. It's just so the gradient first layer, second layer times these two scalars. Of course, you know that these two scalars are converging to deterministic numbers. So when n is very large, this gradient is going to be roughly ID entry-wise. Likewise, for the second layer's gradients, they're going to be roughly ID entry-wise. So when you add them to the initial weights, you maintain the property that the things are approximately ID. And let me just remark that the only reason that these things are not exactly ID is because when width is finite, these guys have fluctuations. And this fluctuation means that like the entries of this gradient will know some information about other entry size, right? Because the size is correlated with the size of these scalars. So that's the only way the entries are not ID, that they can know something about other entries, is through the common fluctuation of their size. But otherwise, if the size becomes deterministic, then everything becomes deterministic, become ID. Okay, so now again, when n is large, you have approximately ID coordinates in the second forward pass. So you can apply the same reasoning as a law of large number behavior for the output network, and so on and so forth. So you can keep reasoning like this by induction, and so you can see that for any finite number of steps for large enough width, then things will become ID. And so for those of you who are more familiar with like the mean field literature, this is nothing really new, and it's the same insight used in the mean field literature to think of the distribution, think of the collection of the weights as like some kind of measure, and then look at the evolution of the measure. So there you think about things in terms of measure, but here we think about things in terms of random variables. But they're two sides of the same coin. But as we'll see, like the random variable perspective is more useful when you go deeper. Okay, so again, my universal claim is that vectors in the tensor program have ID entries when n becomes large, and we can calculate the underlying distributions. I just showed you that things are approximately ID in this particular example, but you can also see that if you know that given that these are like Gaussian, ID Gaussian or something, you can calculate all of these things by taking some expectations and so on and so forth. And like for example, the second layer weight, the second step weights will be linear combinations of the first step weights. So on and so forth. So it's very easy to see that the weights at any given time is, in this particular case, is a linear combination of the weights at initialization. So you can, keep track of the underlying distributions. Okay. So that was the linear case. It's very, very straightforward. When you add nonlinearities, it gets a bit more complicated, but I'm not going to talk about this because I think the amount of insight there is not quite what we want here. Instead, let's go to the linear two hidden layer case. So again, like I want to show you, I want to give you evidence that indeed in these kind of computation, the forward pass, backward pass, so on and so forth, the vectors created have roughly ID entries, and you can track their distribution. So now we go to this deeper case, and I want to continue to show you that this should be true. So, but let's see what kind of difficulty comes up when you try to do this. So in the forward pass, so the network will look like this, right? So again, like you inserted this n by n matrix in the middle. This is the main difference between this two hidden layer case and a one hidden layer case. You don't have this large square-ish matrix. So, so in this forward pass, like everything actually works. It's not hard to see that everything works as intended. Things are roughly ID'd. All the activations are roughly ID. I'll come back to this later, but let me skip over this reasoning part. But let me come to the difficulty when you try to do this in general. So difficulty is when you try to do the backward pass, you see that the gradient of the first layer, for example, looks like this. So it's the transpose of the middle matrix times the upper layer times these two scalars, which are still gonna become deterministic when n is large. But in the next step, you see that to compute an activation, you will have a term of the form, this W matrix times W transpose times the vector, and then some scalars, whatever. These don't really matter. And and this is, so now there's correlation that occurs when you multiply W and W transpose. And this is the a priori somewhat difficult part, where like non-trivial part. Like when you have correlation, it's not a priori clear that the output of this matrix multiplication should have roughly ID entries. I mean, we'll see that it indeed does, but a priori is not necessarily clear. So again, the question is, what do the entries look like? Are they approximately ID? If we can answer these questions in the affirmative, then we can continue to say that yes, we can. All the vectors in the tensor program are roughly ID, and we can keep track of the distribution. But right now, we can see the difficulty, or the temporary difficulty in making that claim, because we don't know how to deal with this yet. Okay, so to summarize, the key question for the general case, the deeper networks, is the presence of these n by n matrices, these square-ish matrices, versus things are more vector-like when you only reason about two-layer neural networks. So the key question is how to reason about WV when V is a vector of dimension n is potentially correlated with the W, the matrix of dimension n by n. So in general, allowing arbitrary correlation, the answer is not very pretty. I mean, you can get for example, V can be like in some eigenspace of W, where a mixture of those things. So it's not very pretty. But we know that V is created from a tensor program, which turns out to force a correlation to appear in a very specific and tractable form, as we'll see in a second. So yeah, to move forward, actually, maybe let me pause now. Like, any questions so far? Yes.
Is this somehow the same flavor as semicircle law?
Yes. So like when we try to discover the form of this guy, the general formula for this will allow you to rederive the semicircle law. So yeah. So the understanding achieved here will kind of cover semicircle law, but semicircle, like things like semicircle law is not sufficient to derive the things we need for neural networks. Anybody else? Yeah.
Not required, maybe, right? Do you need the entire spectrum of the matrix? Or?
So you mean like if I change the spectrum, do I change the results or something like that? Or like the proof techniques?
It seems like you're only using something about the operator norm, whereas semicircle law tells you about the entire spectrum. Do you need the shape of the spectrum and so on here? You probably don't need the shape.
I never use a spectrum in these arguments. So these arguments are purely based on just matrix vector multiplication. What I said about the semicircle law is that you can derive the whole spectrum also through purely reasoning about matrix vector multiplication. That's a commonality between semicircle law and what we're doing here. But you know, like knowing the semicircle law doesn't let you prove the things we want to prove.
You're saying like the power method argument for deriving the semicircle.
So yeah, so you can use TP to prove semicircle law, but it doesn't. It's not the other way around. Okay. Anybody else? Okay, so good. Okay, so the question is, how do you handle the deeper networks? Again, the summary is that these n by n matrices, when they correlate with vectors, a priori is not clear what to do. So maybe just to pause and contrast this. So when you have a like 1 by n matrix, which is just a vector, if it correlates with another vector, like the answer is very easy. Like it's just because their entries look like ID samples from a random variables, and the random variables will correlate. So like so that is very easy to reason about. Just correlation of scalar random variables. But when you have n by n matrices, they don't act like random variables do. So so it becomes more complicated as well. So as a warm up, let's first tackle what kind of what's very straightforward and elementary, which is when you don't have correlations. So consider this cute warm up problem where you have a vector v of dimension n and then w is dimension n by n, the matrix of dimension n by n, and suppose they're independent, where w has entries that are Gaussian with variance 1 over n. Okay. Then condition on v, wv has ID entries, each with distribution 0 mean Gaussian with variance normal v squared divided by n. Okay, so this is just a very routine calculation, using very basic probability theory. So in particular here, when like this expression normal v squared over n converges something deterministic, let's say 1, then wv has ID Gaussian, standard Gaussian entries unconditionally in the limit, right? So this is, so earlier when we looked at the linear network for paths, I said, everything will look ID like fairly straightforwardly. This is the reason, because when you have a matrix multiplied by something that's independent from it, you can reason about its behavior using very elementary probability theory. Okay, any questions? Okay, so now let's look at something non-trivial. So let's introduce some correlation. So the most simple correlation is the kind that we saw earlier from the gradient acting with initialization. So suppose v is an n-dimensional vector, w is n by n, and then with variance 1 over n, Gaussian with 0 mean, like before. But now v is not independent from w, but v in this specific example is w transpose times u, where u is independent from w. So this is like the simplest correlation you can introduce between w and this vector v. Okay. So now let's think about this. Okay, so so show of hands, who thinks it's pretty reasonable to assume that V is independent from W anyway. And so the output of W times V will just be a Gaussian vector. Okay, so who doesn't think so? Okay, so I guess everybody else think it's independent from ZFC. Okay, so let's do some calculations. So let's look at one entry. So alpha here will be an index from 1 to n. So WV at the alphth coordinate, this is entirely trivial. I'm just writing out this matrix of multiplication, right? So WV is W times W transpose times U. So I'm just writing out this this product. So there's a double sum here over two indices, beta and gamma. And yeah, and then so you have this form, okay? So in the next step, what you want to observe is that when gamma equals alpha, there's correlation that occurs between W alpha beta and W gamma beta. So you want to separate this out. So on the left, we're going to separate out the part of the sum where gamma is equal to alpha. So then that will give you W squared alpha beta times U alpha. And because U alpha doesn't depend on beta, I pull this out, okay? And then the remaining part is this guy where gamma is not equal to alpha. Okay, so anybody want to finish the next step? So what happens when n goes to infinity? So the answer proposed is that the second part goes away, and what about the first part? So the proposed answer is that the first term is n01. Yeah, okay, so indeed, this is order 1. I mean, in fact, this is a sum over ID elements, this sum over beta. And the mean is 1 over n, right? I mean, by definition. So this sum, when n goes to infinity, goes deterministically to 1. So this term will be just U alpha when n is large. However, the second term actually doesn't go to 0. So if you do this calculation carefully, you see that this is, so indeed is 0 mean, but the variance actually will converge to something like this. So, assuming like U is like, as standard Gaussian entries, this is like 1. Okay, so the result is that each entry of WV is the corresponding entry of U plus some Gaussian, constant amount of Gaussian fluctuation. Okay. Okay. So yeah. So this is like the summary. So as a vector, WV is like U plus some like ID Gaussian, roughly speaking, when n is very large. Okay. So any questions so far about this? But anyway, the key insight here is that when you do the matmul, you just, again, it's nothing like non-trivial, but you just need to separately reason about when the correlation occurs, where the alpha and gamma are equal, and then when they're not equal. And then the rest is just calculation. Okay, so with this in mind, we can come back to this two hidden layers or 3-layer neural network example, linear network example. And the gradients, will look like this for the first layer. And again, the earlier question was, we were wondering about what happens when you do this W times W transpose times a vector, right? Because we need to reason about this. This is a component of, this is a summand of the middle layer activations. So now the answer is, well, first of all, indeed, the entries are ID as n goes to infinity, right? Because, like what I said here. Okay, there you go. So you know, WV is U, which is roughly ID, and this thing you can just assume it goes to 1. So this is also ID. Right. So everything is ID, and you know, indeed we understand the way it looks. Okay. So you know, this guy will look like something like this. Like you will recall the input to WW transpose, and then add some Gaussian vector to it. Okay, that's what the entries look like. Okay, any questions so far? All right. So now let's add some complexity to it. You know, so we've been just focusing on linear networks for simplicity, but let's be a bit more realistic. So suppose now V is not W transpose times U, but you wrap it around with the phi, with the nonlinearity. Okay, and again, U is independent from W. So now what happens? Let's calculate. So again, this is just a trivial rewriting of this matrix of multiplication. Okay, nothing really happening here. Now what should I do the next step? Okay, so let's expand. How should we expand? How should we do Taylor expansion? Yeah, assuming phi is like smooth or something, like very, very smooth. Okay, how should we do Taylor expansion? Yeah, I mean, that's not a bad first guess. But like before, the insight here is that you want to separate out when gamma correlates, or you know, this part correlates with this part, which is when gamma equals alpha, and when gamma is not equal to alpha. So what you want to do is actually expand around the partial sum, where you know you replace the sum man over gamma with sum man over gamma is not equal to alpha. So expand around this h hat I defined here, which is almost equal to the whole thing. It just differs by this W alpha beta U alpha term. Okay, so this is a Taylor expansion, and you know you note that like this W alpha beta times U alpha is like 1 over square root n or something. So it vanishes as n goes to infinity, and likewise like the higher order terms vanish even faster. So you can essentially just take the first 2 terms. So then it's just straightforward calculation. Like this will look like, you know, like again, you essentially group this part, W alpha beta with W alpha beta, you get this thing. And then the rest of them goes into this part. Okay. Okay, now when n goes to infinity, what happens here? Okay, so earlier, you know, phi prime is just 1. So we just got 1 here because, you know, W squared alpha beta has mean 1 over n. Yeah. So not norm of phi prime, but you just get essentially like the mean of phi prime of h beta. And yeah, so that's right. And then like the second term is essentially a Gaussian term. So the way I write it here is that, you know, you have C times U alpha, where C is essentially the mean of phi prime of h beta over beta. And notice here I replace h prime with h, because essentially here, the difference, the tiny difference between h prime and h does not really matter at all. So you can just replace h prime with h. And then here again, like essentially this is the case where, you know, W is not correlated with the vector coming in. So here you're gonna have like a Gaussian term with variance that's essentially like the norm of V appropriately scaled. Okay, so this is the summary. I mean, essentially the same thing as here. So again, WV is approximately a deterministic number as n goes to infinity, deterministic number times u, which is here, inside the nonlinearity, plus a Gaussian thing. Okay. All right. So this is like maybe 50% of the way there to the general case. But maybe let me pause here in case anybody has questions. Okay, so we're about 50% away there. And then let me just like progressively increase the complexity. We might just skip over some of these because I think we already got the main idea. So the next generalization is multiple inputs to feed. Right, so when you have like V, no, earlier we just have one input to feed. Now let's consider K inputs. Right, V is like this. Okay, what do you think is going to happen? So you feed phi into W. I mean, not quite, because like phi acts across K. Like if you stack them together, then it's like all the things are independent. Like the U1 and U2 are independent, but like here, U1 and U2 can be very much correlated. Okay, so what you get is something like this. Okay, so let's parse this formula. So okay, first of all, there's a Gaussian term, which is again, essentially what you expect if V is independent from W. Okay, so this is the Gaussian term that will be what you guess if you naively assume things are independent. And then there's a term that accounts for the correlation of W and V. Accounts for the fact that V already knows about W because V was created from W transpose. So again, a priori, like this term could be very complicated, where it's not even like additive between the first part, the correlated part, and the non-correlated part. But somehow these are actually additive, and in fact, the correlated part is actually a linear combination of these vectors U1 to UK that went into W transpose. So the precise formula is similar to before. You essentially take a derivative of V against the corresponding input, and then you average over the neuron dimension. And then this would converge to something deterministic when the width n goes to infinity. Okay, so yeah. Okay, so so let me just quickly go over the most general formulation. This, I think we already got kind of the flavor of things, so I'm not going to belabor the point too much. But essentially the point, the form at the end you're going to get is that for every vector, you can associate a random variable, ZV, such that as n goes to infinity, V's entry will look like ID samples of the ZV. And then you can like, for the rules of tensor programs, which are cornerwise nonlinearity and matrix multiplication, you can track how these random variables ZV will evolve. So first of all, if you wrap V around with a nonlinearity, then that you can just pull that out of the superscript. Right? So Z phi V is phi ZV. That's very natural. It generalizes multi-input nonlinearities. The less obvious one is the thing we've been focusing on, which is matrix multiplication. So if you have ZWV, if you have W times V, W can be correlated with V through the computations in the program. So again, we need to reason about like how the correlation can occur. And just as before, like you can decompose this random variable into two parts. One is the Z hat, this term is essentially the Gaussian term, which you would guess if V and W are independent. And then the first term is where the correlation comes from. So I'm writing this weird looking formula, but you can essentially notice there's a derivative in here, and then you're taking expectation, which is what the averaging becomes when you let n goes to infinity. And then there's like random variable on the outside, which corresponds to the vector before. So, so like here, this is the example we saw. If V equals, phi H and H equals W transpose U, then WV looks like, a linear copy of U plus a Gaussian part, which is what this is. So the Gaussian part corresponds to Z hat, and CU corresponds to Z dot term. Okay, so let's not dwell on this too much. You can generalize this further. Okay, so let me try to wrap up. So the key insights of tensor programs we talked about in this last lecture is the two things here. So the fact that every deep learning computation is composition of two building blocks, matrix multiplication and coordinalized nonlinearities, starting from ID random initialization. So this is essentially the definition of a tensor program. And you can essentially write anything you write in PyTorch in this form. And once you have this program, the insight here is that every vector in the tensor program have ID entries when n goes infinity, and we can calculate the underlying distributions. So this in particular means that, for a neural network, you can train it however you want. Then no matter how you train it, the activations of the neural network, the inside of the neural network will have roughly ID entries, right? And furthermore, you can calculate what the entries look like, and from that you can also calculate what the output of the network looks like, and so on and so forth, what the loss is, and so on and so forth. So now you have this foundation. The key thing, the cool thing now is that you can take the infinite width limit of anything. And before, it's really like very labor intensive to derive the infinite width limit of any particular thing. Now this is like a walk in the park. And so for example, before, so this is a diagram showing the unrolling of the gradient descent of a neural network, where this is a forward pass, and then this is a backward pass calculating the gradient, and then the second forward, second backward, so on and so forth. And so in the 1990s, Raffer and Neal derived the neural network Gaussian process, which is essentially just looking at the first forward pass. This is the easiest thing to do because everything is independent. You don't have to keep track of any correlation. And then recently there's the work on your tangent kernel, which is roughly like looking at the first backward pass. It's a bit more than that, but roughly speaking, that's essentially it. And here is slightly more difficult, but still easy because there's essentially no correlation in the weights. And then Linnaeus et al. Looked at two-layer neural networks, but for multiple steps in this mean field limit, which is like the baby version of feature learning limit. And that is a kind of a special case that allows you to reason about things in terms of like Wasserstein gradient flow. That allows you to unwind the SGD. But in the general case, this is like quite a jump. The mathematical machinery. But now we can do it. It's just follow the rules, and then you can do the calculation. So the general feature learning limit, which is the limit of infinite width limit of mu p, you put everything you care about in the box, and then you take the limit of the whole box. The box being the pre-training of GPT you want, and then you can calculate this limit. And this is what allows us to derive this picture. Okay, so I didn't really tell you directly why the picture looks like the way it is, but I told you essentially all the machinery that will allow you to do actually the work that would tell you what the picture looks like. Whereas before, like the foundation is not even there, so you cannot even imagine how to answer this question. Okay, so this is essentially a summary of the tech stack with the stack of mathematics that we went through in the series of 3 lectures. So again, in the beginning, the first lecture, I talked about mu-p, why empirically so great, and then this lecture I talked about some intuitions, the mathematical intuitions behind it, and then it's derived from this dynamical dichotomy theorem. And then this lecture I gave you some of the taste of the underlying foundational mathematics that was required to prove something like this, or to even suspect something like this. Okay, so hopefully that is a good dessert. So finally, I'll just kind of take a look at the larger picture. So let me step back, right? So like, these two things, Manhattan Project and space program, are some of the greatest triumphs of 20th century science. I mean, for good or bad. But what I actually want to focus on here is that, like scientifically, they have a very interesting, a very particular characteristic, which is that, they are very expensive empirically. Like, each atomic bomb costs, I don't know, like at least, definitely near $1 billion or more of the, adjusted for inflation or whatnot. Space program likewise. So each empirical test is very expensive. So, if you want to, launch a rocket to space, you can't just be like, oh, let me just like make, 100 rockets and then try like different propulsion coefficients until you lands on the moon. I mean, no astronaut's going to sign up for that. Likewise, for Manhattan Project, it's expensive in cost, and also, can be dangerous to humans. So you cannot just, keep firing bombs until you get it. So this requires extensive theoretical calculation first before launching any empirical tests, like in various flavors of theoretical calculations. I mean, of course, like for the space program, if you don't know Newton's laws, okay, there's no game to play at all here. And now we're in a new phase of our civilization where we're getting close to human level intelligence, for better or worse. And these are driven by these large foundation models, and they have the same characteristic of requiring, having very expensive training runs. Each training run right now costs maybe $10 to $100 million per training run, which is still like at least 10 times smaller than the other projects. But it's getting more and more expensive because people are training larger and larger models. So this is also an area where theoretical calculations are crucially needed, because you don't want to waste your empirical tests. You want to use them very efficiently. So this question of training large models reliably and optimally is a very critical question. I mean, I think you'll be pretty fair to debate whether this is indeed a space program of 21st century. So that brings us to this cartoon. I think this is like taking a further step back. So I kind of think about the role of theory in some kind of cartoon like this. So in this cartoon, you have problem scale on the x-axis and the cost of insight on the y-axis. So if you look at the empirical insight needs to do experiments. So that means that as the problem gets larger, each experiment costs more. So the cost of insight goes up linearly in terms of problem scale. On the other hand, a purely theoretical insight has costs that's independent of problem scale. We can think about a large number of like gas particles, if you want, like without actually having to create individual gas particles by themselves. So like a pure theorist, a pure mathematician doesn't care about how large the problem is. So if you look at very small problems, I mean in deep learning maybe like CIFAR 10 scale problems or something like that. Then there's almost no reason to do theory here. You can just like spam experiments until you get the right thing. But for things like large scale pre-training like GPT, theory is super critical, because if you get the right insight, it's humongously much more cost effective than empirical insight. I mean, it is empirical insight is still important, but theoretical insight can be much more cost effective. And then space program costs even more. And of course, again, like if you don't have Newton's law, there's nothing to talk about. So TP and MUP is kind of this fortunate intersection between theoretical insight and some large scale problem. But this is really like a very fertile ground for theoreticians and mathematicians to work on, and it has like enormous impact on our world. And I myself believe that the beauty of the work essentially eventually comes from the amount of impact it has. I mean, for more or less, like all the stuff on string theory, in modern day, all comes from because like Einstein did something in the past that had impact. Cool. Yeah, I'll just end here. Happy to take questions.
So are there any non-asymptotic ways, or have people tried to prove it? So like in NTK, earlier it was for the analysis was asymptotic, but then people tried to give
Yeah.
non-asymptotic assumptions, right? So
Yeah.
is there anything for this as well? I mean, mu-p as well.
Yeah, I mean, it's very doable here. I mean, you can definitely prove non-asymptotic results. I haven't I myself am not that interested in non-asymptotic results because I can already predict what I want to predict with asymptotic results, and non-asymptotic results doesn't really tell me anything new. I mean, at least the things I care about. But I mean, it's very doable. Like I mean, at least like I can sketch the proof for you, but I just don't. It's not my priority, I guess. But it's very doable, you know. And like it's I mean, you just have to like reason about things inductively, to structure the program inductively. But yeah, it's pretty doable.
Thank you.